This is the momentum unit, video 1. There is quite a lot to do with momentum. It's one of the bigger topics in physics. So we have our big idea 1. Objects and systems have properties such as mass and charge. Systems may have internal structure. So what that means is we're going to deal with objects interacting with each other inside a larger system. Big idea 3. The interaction of an object with other objects can be described by forces. So we're going to talk about forces and how objects, maybe hit each other or whatever, just so that there's forces involved. Interactions between systems can result in changes in those systems. So we're going to talk about how objects can interact with other ones. Changes that occur as a result of interactions are constrained by conservation laws. So there's going to be a conservation of momentum law that we have to deal with as well. Quite a few learning goals for this unit. I want you to be able to explain what is needed to calculate relationships between changes in momentum, average force, impulse, and time of an interaction. I want you to be able to calculate the change in linear momentum of a two-object system with constant mass and linear motion from some sort of representation of that system. I want you to be able to apply mathematical routines to calculate the change in momentum of a system by analyzing the average force exerted over a certain time. I want you to be able to define open and closed systems for everyday situations and apply conservation concepts to those systems. It's kind of like what we did with energy. I want you to be able to use concepts of kinetic energy to describe a collision as elastic, inelastic, or perfectly inelastic. And I want you to be able to predict the velocity of the center of mass of a system when there is no interaction outside of the system, but there is an interaction within the system. So quite a few learning goals for this one. But we're going to take our time with it. We're going to get lots of practice in class. So to get us started, what exactly is momentum? Well, to help you understand this, a rhetorical question here. Would you rather be hit by a child running into you or by a large car traveling with the same velocity? Obviously the child. The child has less hitting power than the car, even though they're both moving at the same velocity. And it comes down to the fact that the child has less mass. So momentum is something that depends on mass along with velocity. So momentum, which we represent with a lowercase p, equals mass times velocity. This is our definition for momentum. And notice we got some scalar multiplication here. So take a vector times a scalar, that returns a vector. So mass is a scalar, velocity is a vector. The units for momentum will be the kilogram meter per second. There's no fun derived unit for momentum. It's just simply a kilogram meter per second. Now this concept of momentum was kind of created by Newton. Newton observed the properties of inertia, the fact that objects in motion stay in motion, objects at rest stay at rest, and he correctly found out that this properties of inertia depends on the mass and velocity of an object. So let's say we have something has a changing momentum. So some knowledge here, the change in momentum of an object is a vector in the direction of the net force exerted on the object. So to help us understand that, let's take a look at something called the impulse momentum theorem, and let's take a look at two asteroids colliding. Now I chose two asteroids because there are no other forces acting on them. So let's say I have one asteroid. It's moving. And I have a second asteroid. And it's moving. So both of these have initial velocities. So they're both moving. And obviously they're going to collide. So when they collide, that's an interaction. They're interacting with each other. So asteroid 1 is going to exert a force on asteroid 2. And asteroid 2 is going to exert a force on asteroid 1. So this two asteroid system, they're interacting. So there's two forces inside. So these are interaction pair of forces. These forces are equal in strength, opposite in direction. They do not cancel each other out because they are two forces acting on two distinct objects, all within that same system. Now, after these two asteroids collide, let's say they bounce off each other. So they're going to move away with some final velocity. So that's our situation. These two asteroids come at each other, they hit, bounce off, and go away. So we want to be able to study what's going on. So let's begin by just taking a look at asteroid number 1. Asteroid number 1 had its momentum change. And the reason why was because it had some final momentum and some initial momentum. So it had the final momentum, which is mass times velocity, minus mass times velocity. And by taking a look at the final momentum minus the initial momentum, we see that object 1's momentum changed. What I'm going to do now is I'm going to divide both sides of this equation by time. And the reason why I do that is because I want you to recognize that on the right side of this equation, I can factor out the mass, and I'm left with final velocity minus initial velocity. Well, that's like a delta V. So I have a delta V divided by a delta T. That gives me acceleration. Okay, well, mass times acceleration, that's the same thing as a net force. And if I look at my scenario, there was only one force acting on that asteroid 1. That was at force 2, 1. So what I'm left with is change in momentum for object 1, respect to time, equals the net force, which was at force F2, 1. So the force provided by object 2 acting on object 1. I can then rearrange this. Excuse me there. And this gives me something called the impulse momentum theorem. So what this says is that the change in object 1's momentum equals the net force acting on object 1 multiplied by a time interval. Now notice I could do the same exact math for object 2. And basically, if you want to, you can work out that math, but you get the same thing. Now, this force multiplied by time, that is called impulse. So impulse, which we represent with a J, it's a vector, equals like a net force acting on an object multiplied by time. The impulse can be positive or negative. So if I have something moving in a positive direction that has a negative impulse acting on it, that object will slow down. Or if I have a object moving in a positive direction and it has a positive impulse act on it, it will speed up, it'll accelerate, it'll get faster in a positive direction. So what we can gather from this is that the change in momentum of an object occurs over a time interval. There's no instantaneous, so the time interval can be really short or it can be long. The force that one object exerts on a second object changes the momentum of the second object. And then the change in momentum of that object depends on the impulse, which is the product of the average force, or net force, and the time interval during which the interaction occurred. So, F delta t, that is our impulse. And then, like I said before, together with the change in momentum, we create something called the impulse momentum theorem. So what would this look like on a graph? If I were to make a plot of force versus time, and let's say I'm looking at between some initial time and some final time, the area, well, actually first, slope. If I take a look at the slope would have units of newtons per second, which really, I can't think of anything. I can't really think of anything that would represent. The area would have units of a newton times a second. Well, a newton is a kilogram meter per second squared. So if I take a newton times a second, that gives me a kilogram meter per second, which equals momentum. Or impulse. Because remember, the change in momentum equals force delta t. So momentum and impulse have the same unit, a kilogram meter per second, or a newton times a second. So the area between the line and that axis gives us the impulse. This really, what this boils down to is it helps us understand some sports in many ways. If you're in sports, your coach probably tells you a lot of the times to follow through. And what this means is that, a small force with a long contact time can have a greater change in momentum than a large force with a shorter contact time. So follow through, that's why it's so important. If you extend the amount of time that you're in contact with that ball, you will give that ball a greater change in momentum, making it fly farther. Now we can also do a quick little restatement of Newton's second law. So the impulse momentum theorem says that the change in momentum equals a net force multiplied by a time interval. So if I do some quick rearranging here, I see that the net force equals the change in momentum with respect to time. Momentum is mass times velocity. So I get the mass times final velocity minus mass times initial velocity. Make sure those are all vectors with time. And again, I can factor out the mass, so I see that the net force equals mass times change in velocity with respect to time. Change in velocity over time is acceleration, so I see that the net force equals mass times acceleration. Now, it's important to realize that Newton originally never said F equals ma. He never said that. What Newton did say was that a net force is equal to the derivative of momentum with respect to time. This is originally how Newton said his second law. and of course going to algebra-based physics, the d's become deltas. So that is the original Newton's second law, change in momentum with respect to time. All right, that's going to conclude video 1.